Good morning. Now this is the continuation of our last class on the session first law of thermodynamics. Now in this class we will learn about indicator diagram and work done during isothermal expansion and adiabatic expansion of an ideal gas. So let us begin with indicator diagram. Indicator diagram or PV diagram means it is a graph that is drawn between volume along x-axis and pressure along y-axis. This graph helps us to find the work done by the system. Now suppose that a system is at initial state 1 and suppose that it is taken to the final state 2 along two different paths, that is path A or path B. So a system in initial state 1 can be taken to its final state 2 either through path A or through path B. Okay, now here let P be the pressure and V be the volume. So CD will be equal to P and OD is equal to V from this graph. Now consider a very small expansion in volume, say dE. This is a small expansion in volume, let that be dV. And now this volume expansion is considered to be so small that the pressure P remains constant. So now the expression for work done during this infinitesimal expansion in volume dV is equal to P dV, and that is nothing but the area CDEF. Okay, now the total work done by the gas during the expansion from state 1 to state 2 along path A will be represented as WA is equal to small work done, that is dW along the path A from the initial state 1 to the final state 2. Okay, so dW we can say that it is PdV along the path A from initial state 1 to final state 2, and that is nothing but area 1A2HG1. That is area this one 1A2HG1. Okay, so when a system is taken from initial state 1 to final state 2 along the path A, then the work done will be equal to 1A2HG1 or area enclosed by that region, that is 1A2HG1. Now we have already said that there is another path, say B. Okay, so similarly for path B, it will be WB is equal to dW along the path B from 1 to 2. It will be PdV 1 to 2 along the path B. And in such cases, if the system is taken from state 1 to state 2 along the path B, then that work done will be given by area under the curve 1B2HG1. See, it will be 1B2HG1. Okay. The area under the two curves A and B are different. So the work done, the amount of work done will also be different. That is quite evident because values of W and WB are different. So we can say that work cannot be expressed as a difference between the values of some property of the system in two states. This means that work cannot be considered similar to temperature or pressure of a system. Okay. So when a system changes from a state to another, amount of heat transferred will depend upon the path taken. Okay, that is in the case of heat. So now here it is seen that both heat and work are not point functions, that is they are path functions and both depend only on the process. So from this the conclusion that we reach is that work done in taking the system from one state to another will be different for different paths. It's quite evident, that is when we have taken the system along the path A, work done is given by area 1A2HG1, whereas when the system is taken from state 1 to state 2 along the path B, area work done is given by the area 1B2HG1. So both these areas, the values are different. So from which it is very clear that work done in taking the system from one state to another will be different for different paths. Now work done in a reversible process. Here we have already seen that the definition for PV diagram. It is nothing. The relation between pressure and volume of a system undergoing a change can be represented by a graph. In that graph, we take volume along x-axis and pressure along y-axis. This graph is PV diagram or PV curve, and work done during the process by the system is obtained from this graph. That is the significance of PV diagram. That is, work done by the system during a whole process can be obtained from this PV diagram. Here also has the same explanation. Let AB be the indicated diagram for a reversible process. We are considering a small expansion in volume dV, and let that be represented by EV, the region EV on that graph. Now the pressure P will be equal to EG, because for that small expansion in volume, pressure is supposed to be a constant, and that is equal to EG. Okay, so work done will be dW is equal to PdV. So pressure we know it is Eg. So Eg into dV. What is dV? EF. So work done dW, that is small amount of work done during the small expansion volume, will be equal to dW is equal to area EGHFE. Okay, that is shaded portion EGHFE. Now suppose that V1 and V2 are the initial and final volumes. Now total work done will be, you have to integrate. So W will be equal to V1 from V2 PdV, and that is nothing but the area enclosed by the loop ABCD. A. Okay, so area enclosed by the PV diagram gives work done during the process. So what is PV diagram? It is a graph that is obtained by plotting volume along x-axis and pressure along y-axis. Now the significance is that area enclosed by the PV diagram will give you the total work done by the system during a process. Now this is an important one. Work done in a reversible isothermal expansion of ideal gas. This is a derivation that is most probably asked. Now here the small expansion in volume, let that be dV, and so small amount of work done is dW is equal to PdV, that we have already seen. And now suppose that the volume of the gas that we are considering changes from V1 to V2, then total work done W will be, you have to integrate dW, that is integrate from V1 to V2, initial volume to final volume PdV. Now you know that PV is equal to RT, ideal gas equation. From that, what is P? This one. So this expression W will be now reduced to this one. Instead of this P, we have to use this one, that is RT by V dV, and RT is a constant, so it's taken out. Then integral V1 to V2 dV by V. What is integral 1 by V? It is log V. Okay, so RT log V, V1 to V2, so RT log, applying the limits V2 by V1. And now in order to make this log E, you have to convert it to log 10, you have to multiply with a constant, that is 2.3026. So the final expression for work done by a ideal gas during isothermal expansion is 2.3026 RT log to the base 10 V2 by V1. Okay, it is a very simple derivation. Now we know that PV equal to RT. So P1 V1 will be equal to P2 V2, and that will be equal to RT. So from this equation, what is V2 by V1? It will be P1 by P2. So in place of equation 1, instead of V2 by V1, we can also write P1 by P2. So you will get another expression as W is equal to 2.3026 RT log 10 P1 by P2. See, that is this expression. Now next derivation is work done during a reversible adiabatic expansion. This one was isothermal expansion. Now it is adiabatic expansion. Similar expressions, that is, let there be a small expansion volume. So small amount of work done will be dW. dW is equal to PdV. So in order to find the total work done, we have to integrate. So that W will be integral from V1 to V2 PdV. Now we have already seen an adiabatic equation in the earlier session, that PV gamma is equal to K, a constant. You have to make use of this property. From this, P is equal to K by V raised to gamma. Okay, so in place of this equation, you have to write in the above equation, in place of P, you have to write K by V raised to gamma dV. K is a constant, it is taken out, and what is remaining is integral V1 to V2 dV by V raised to gamma. Okay, now V raised to dV by, that is 1, this is same as 1 by v raised to gamma. So 1 by v raised to gamma can be written as v raised to minus gamma. That is written here. Okay. And now k is again taken out. Now what is integral x raised to n? X raised to n plus 1 by n plus 1 by n plus 1. Okay, that was the formula. So applying that, this one will be v raised to minus gamma plus 1 by minus gamma plus 1. We limit v1 to v2. Now k by the denominator is taken outside. What is the denominator? Minus gamma plus 1. It is same as 1 minus gamma. So k by 1 minus gamma is taken outside, and this one v raised to 1 minus gamma is kept as such, limit from v1 to v2. Okay, now here you are going to apply the limit, that is k by 1 minus gamma is kept as such. Here you are going to apply the limit. So it will be the first limit v2. So it will be v2 1 minus gamma minus v1 1 minus gamma. Now this is the adiabatic equation, that is p1 v1 raised to gamma equal to p2 v2 raised to gamma equal to k, because pv raised to gamma equal to k is the adiabatic equation. So you are just writing p1 p2 and v1 v2. Okay, same equation. So again, this equation will now become w is kept as such, 1 minus gamma is here. Now in place of k, this k is taken inside. So this will be k v2 1 minus gamma. So here in place of k we are using this term first. So in the place of k you are writing this one, p2 v2 raised to gamma, and v2 1 minus gamma is kept as such. Now again this k is taken here also, that is k v1 1 minus gamma. This v1 1 minus gamma is kept as such. So this k, this is actually k. So in place of that we are writing p1 v1 raised to gamma. Okay, now this is kept as such. Here this will be p2 v2. Why? Because v2 gamma and v2 1 minus gamma, this one will get cancelled. So what remaining will be only v2. Okay, because when you split up v raised to v2 gamma, v2 1 minus gamma means v2, then v2 minus gamma. So this and this will get cancelled. So only v2 will be there. Similarly here. So the expression will be w is equal to 1 by 1 minus gamma p2 v2 minus p1 v1. You can just work it out on a paper, then only you will be able to understand, because all these are simple calculations. Now again p2 v2, in place of that pv is equal to rt, ideal gas constant, right? So here what will be p2 v2 rt2, what is p1 v1 rt1. Okay, now r is taken outside, what remaining is t2 minus t1. Now, what is gamma? Gamma is actually the ratio of specific heat capacity at constant pressure, that is Cp, divided by specific heat capacity at constant volume Cv. So, gamma is Cp by Cv. So, what is gamma minus 1? Cp by Cv minus 1. It is nothing but Cp minus Cv by Cv. But Cp minus Cv is R. That derivation we have studied in the last class, that is universal gas constant. Cp by Cv is gamma, whereas Cp minus Cv is R. So it is R by Cv. Okay, now you write that expression. So equation from equation 4, W is equal to R by gamma minus 1 T1 minus T2. Now here you have to substitute for gamma minus 1. So we have obtained that gamma minus 1 as R by Cv. So you have to substitute here R by Cv. So R and R will get cancelled. What remaining will be Cv. So W is equal to Cv T1 minus T2 is the work done by an ideal gas during adiabatic expansion. Okay. So these two derivations are very important, and isothermal, this indicator diagram is also very important. So this session is important. So please read through. Okay, thank you.